Hello, good afternoon everyone. So dear students, today's topic is bioreactors and its types. Now coming to the definition of a bioreactor. A bioreactor is a vessel in which a chemical or biochemical process is carried out which involves organisms or biologically active substances derived from such organisms. Bioreactors find diverse applications in various fields of life. For example, for production of vaccines, proteins, organic acids, amino acids and antibiotics, enzymatic or microbial biotransformation can also be carried out using bioreactors. Now it also finds importance in bioremediation of xenobiotics, etc. Now production industry usually has a chain of bioreactors. It is not a single bioreactors which can give you the product. You have to follow a stepwise scale up of the reactor size, and a train of bioreactors may be required ranging from 20 liters to 2,50,000 liters or more. The bioreactors are arranged in a series of increasing sizes, starting from the small cultures to the final production culture. Now, depending upon the requirement, there are many types of bioreactors which can be applied to the production process. The first is of reactors which are called as stirred tank reactors. This type of microbial reactors have impellers to provide agitation and generally have 4 baffles from the walls to prevent vertexing of the fluid, and the baffle width is usually between 1/10 to 1/12 of the tank diameter. The vortex and circular flow result in a little mixing between the fluids at different heights. Means the fluid which is present inside the fermenter is mixed with a different rate, with different velocity depending upon the distance from the bottom of the tank. At high speeds, the vortex may reach down to the impeller so that the gas from the surrounding is drawn into the liquid, causing high mechanical stress in the stirrer shaft, bearing and seal. Bioreactors for animal cell cultures usually do not have baffles. Why? Because the baffles may break the animal cells, which are very fragile and they are not hardy like the bacterial cells or the plant cells which have a cell wall. You know that the animal cells, they lack cell walls, so they are just having the plasma membrane to enclose them, and the plasma membrane is very delicate, so it can be broken down if we use a fermenter or a bioreactor which has baffles. And due to the turbulence, the cells may break. So for animal cell bioreactors, we do not have baffles in the design of the fermenter. Now the aspect ratio is a very important term. Aspect ratio is the ratio of the height of the diameter, height of the fermenter to the diameter of the fermenter, that is the vessel, bioreactor vessel, and it is between 3 to 5 for microbial cultures, but it is normally less than 2 for the animal cell culture. What does it mean? Height to diameter ratio is less in case of animal cell culture. What does it mean? That means that the height is less than the diameter in case of animal cell culture. Means height is very less as compared to the bioreactors which are used for microbial cultures. In case of animal cell culture, we use a fermenter with a less height, and sterile gas is passed at the bottom using a perforated pipe ring sparger. The number of impeller depends upon the aspect ratio. The bottom impeller is located at a distance of 1/3 of the tank diameter above the bottom of the tank. Then additional impellers can be used which are spaced approximately at a distance of 1 to 2 impeller diameter from each other. And the superficial aeration velocity, that is the volume of flow rates of gas divided by the cross-sectional area of the vessel, is called as the aeration velocity. In the stirred vessel must be lower than that can flood the impeller. An impeller is flooded when it receives more gas than it can effectively disperse. Otherwise, the mixing is poor. And superficial aeration velocities generally do not exceed 0.05 meters per second. Now coming to the impellers. The choice of impellers often depends upon the viscosity of the liquid and sensitivity of the cells to mechanical shear. For example, there are 4 types of impellers usually used, which are normally used. First is Rushton or disc turbine impeller, which has a 6 flat blade design. Then second type is concave bladed impeller, whose diameter is about 1/3 of the vessel diameter, and it is often used for bacterial cultures. And then next is the hydrofoil impeller, whose diameter is 0.5 to 0.6 times of the tank diameter, and it is an effective mixer of the marine impeller. It is usually singly present and it has a large diameter. Hydrofoil impellers they are characterized by a large diameter. Then the last type is marine impeller, which is also very large in diameter, and it is usually single and it often contains 3 blades. Now you can see the different types of impellers which are used in a stirred tank reactor, and pay attention to the design of the stirred tank reactor, which has sparger in the bottom of the fermenter vessel. Then there is a centrally placed shaft which contains impeller blades extending from it, and you can see this figure contains 2 sets of impellers, and which are at 1 to 2 diameter apart. And in the side you can see 2 structures which are called as baffles. And the flow pattern depends upon the type of impeller which you use. For example, in case of Rushton turbine impeller, you get a double type of flow which you can see. First is clockwise, and half of the vessel has anti-clockwise movement of the liquid. But in case of the marine impeller, you have only one type of movement throughout the vessel. Impeller speed. It is usually between approximately less than 120 rpm for animal cells, and impeller tip speed is 3.14 into impeller diameter into speed of rotation, and it is numerically less than 7.6 meter per second for filamentous fungi, and similarly it is also less for the animal cells as compared to the bacterial cells. Now coming to the power requirement, which is a vital parameter for running a fermenter or a bioreactor. It is critical for the large scale bioreactors and smaller for the spatched reactors, because the gas bubble decreases the liquid density and the gas filled cavities develop behind the stirred blades, which reduce the resistance to fluid flow and decrease the drag coefficient of the impeller. The formula for the power requirement is as P0 is equal to Np into rho I into Ni to the power 3 into 3 Di, where P0 is the power input, Pi is the density of the liquid, Ni is the rotational speed, Di gives the diameter of the impeller, and Np denotes the power number. Actually, this PL which is written here is the rho L. So it should be denoted by the symbol rho. Rho denotes the density, as you all know. Then coming after the stirred tank reactor, which is the most common type of reactor, the second type of reactor is bubble column reactor. This bubble column reactor, as the name signifies, has main driving force as the bubbles which are pumped via the inlet. Air is pumped through the inlet in the bottom, and this sparging of air creates big bubbles, which helps in the aeration and more rate of oxygen transfer. It causes greater mixing, and other performance factors are influenced mainly by the gas flow rate and the rheological properties of the fluid. Now, mixing and mass transfer can be improved by placing perforated plates or vertical baffles in the vessel. Third type of reactor is the airlift bioreactor. This is separated as two zones. First is the sparged zone, which is called as the riser, and the zone that receives no gas is the downcomer. The bulk density of the riser region is lower than that of the downcomer region, causing the circulation. So the circulation is due to the difference in the bulk densities of the riser and the downcomer regions. For optimal mass transfer is the generation of biomass from the nutrients which are present in the culture medium, which is provided in the vessel, so that nutrients or the carbon sources, they are converted into the biomass. So this is called as the mass transfer. Now, airlift bioreactor. You can see the design of the airlift bioreactor, where you can see the riser and the downcomer regions, and there can be three types of designs based upon the relative position of the downcomer and the riser. You can see the riser is in the center in the first vessel, whereas in the second type of design, more than half of the vessel is consisting of the riser, and about 1/3 of the vessel comprises of the downcomer column. Then in the third type, it has a circular motion, and riser and the downcomer are separated by a oval space. Then third is fluidized bed reactors. What are fluidized bed reactors? It consists of a vessel which is filled with some solid substrate, solid support, and in between the nutrient fluid or the media is filled. So it is suited for the reactions involving a fluid suspended particulate biocatalyst, such as immobilized enzymes and cell particles. This is similar to the bubble column reactor, except that the top section is expanded to reduce the superficial velocity of the fluidizing liquid. The top section is expanded to reduce the superficial velocity of the fluidizing liquid, and a level below that needed to keep the fluids in suspension. Consequently, the solid sediment is expanded in the expanded zone and dropped back. Consequently, the sediment in the expanded zone and drop back. Hence, the solids are retained in the reactor, whereas the liquid flows out. In the fluidized bed reactor, the liquid containing the product is taken out or it flows out through the outlet, whereas the solid support or substratum remains inside the bioreactor after the reaction is complete. This is the design of a fluidized bed bioreactor. Here you can see the biocatalyst, which is usually a immobilized enzyme coated on the beads. You can see the beads. So these beads can be solid or they can be porous. Then fifth type of bioreactor is the packed bed bioreactor. It has a bed of particles that are confined to the reactor, and the biocatalyst is immobilized on the solids, which may be rigid or macroporous particles. But only difference between the fluidized bed bioreactor and the packed bed bioreactor is that the fluidized bed bioreactor contains a greater head space, which is a very wide space just above the bioreactor, which is filled with the liquid. Whereas the packed bed bioreactor is a closed vessel having uniform diameter throughout. A fluid containing nutrients, it flows through the bed to provide the needs of the immobilized biocatalysts, and the metabolites and products are released into the fluid and they are removed in the outflow. You can see there is a outlet at the bottom for the harvesting of the products, and the flow can be upward or downward. Means the media can be supplied from the bottom, or it may be poured from upside. Both cases are possible. You can use both the ways. The flow can be upward or downward. If upward fluid is used, the velocity cannot exceed the minimum fluidization velocity. Now, based upon the content of my presentation, there are numerical problems, and which are very easily solved if you know the formula. For example, first problem is for an E. coli culture in an exponential phase of growth, OD at 540 nanometer is 0.3. 0.3 at 2 hours. I forgot to write 2. Is 0.3 at 2 hours and 0.6 at 4 hours. Assuming that the OD is linearly proportional to the number of E. coli cells, the growth rate per hour of the culture is, so the answer is 0.5, because the formula is growth rate is 1 upon the doubling time, and here the doubling time is 2 hours. So 1 upon 2 hours becomes 0.5 hours. Then the second numerical is at the end of a batch culture, glucose solution is added to the vessel at a rate of 200 ml per hour, and the culture volume after 2 hours of glucose addition is 1000 ml. The initial culture volume in milliliters is, and this question was asked in the GATE exam of biotechnology in 2018, and here the answer is 600 ml. Why? Because the volume of externally added glucose at 2 hours is 400 ml, and the total volume of the vessel is 1000 ml. So the volume which was already present is naturally the difference between the externally added glucose and the total volume, which is 1000 minus 400 ml, that is 600 ml. So these are very simple numericals which you can practice. Then one more question. The first order deactivation rate constants for soluble and immobilized amyloglucosidase, the enzyme name doesn't matter, you just see the values which are given, that is 0.03 per minute. So the rate constant is 0.03 per minute and 0.05 per minute. That means the Soluble enzyme has 0.03 per minute and immobilized enzyme has the rate constant of 0.05 per minute respectively. The ratio of the half-life of the immobilized enzyme to that of the soluble enzyme is, so the answer is 6. Then the power required for agitation of non-aerated medium is, so all the parameters are given, and I have told you the formula for the power requirement P0 was, I am coming to the formula. Using this formula, P0 is equal to NP into rho L into Ni to the power 3 into 3 Di to the power 5. So when you put these values, when you substitute these values in the above formula, you get the answer as 625. So this was all in short about the types of bioreactors and the problems based upon their design and power requirements.